There's so much time.
Yeah, right. Yeah, that's correct. So we're looking at electrostatics, and electrostatics is a very short part of physics. But we're looking at the June 2023 past exam question 7. And we are effectively then saying there are 2-point charges X and Y. Right, 2-point, we call them point charges X and Y. They're distance of 0.03 meters apart from each other. Right, and 1-point charge is negative 7.2 times 10 to the minus 9 coulombs. And the other one is plus 7.2 times 10 to the minus 9 coulombs. And we proceed to state Coulomb's law in words. You proceed to state Coulomb's law in words, and we then say the solutions. The solutions. 7.1. Okay, now looking at these, what does Coulomb's law say? And what is the actual official way of stating Coulomb's law in the exam? And we must study this very carefully. How do we state Coulomb's law in words for the examiner to give us full marks here? We state the law as follows. The magnitude. We say the magnitude. Right, so the magnitude of the electrostatic force. Of the electrostatic force. Exerted. Right, exerted by 1. Right, by 1 stationary. Right, stationary. Point. Point charge. Point charge, Q1. On another stationary point charge. On another stationary point charge, Q2. Is directly proportional. Right, is directly proportional to the product of the magnitudes of the charges. And inversely, proportional to the square of the distance are between them. Right, between them. So we are saying, so we are stating Coulomb's law in words. What does Coulomb's law say in words? The magnitude of the electrostatic force exerted by one stationary point charge, Q1, on another stationary point charge, Q2, is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. We read again. The magnitude of the electrostatic force exerted by one stationary point charge, Q1, on another stationary point charge, Q2, is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance r between them. Okay, so that is what we call Coulomb's law. And now we look at the next question. Draw the net electric field pattern due to X and Y. What is the net electric field pattern due to X and Y? We look at 7.2. We look at 7.2. Okay, so here is X. And here is Y. So we know, therefore, that at this point, X is negative. We know that Y is positive. So if you put a negative point charge and a positive point charge, they attract each other because they are oppositely charged. We say opposite charges attract. So a negative and a positive attract each other. When they do, there is then an electric field pattern, and the examiner is saying you need to draw. You need to draw. So we put a drawing of the net electric field pattern due to X and Y. So we draw. How do we draw? We draw like so. Right. So we draw like so. Like this. Okay. We draw like so. So yeah. Okay, so now what is happening is, therefore, the direction of charge is from positive to negative. From positive to negative. So now here, because this one is negative, they go in the directions. They go towards. But on the positive end, they go out. They go out. Like this. Right, so this is exactly what the examiner wants here. So because they said, draw the net electric field pattern due to X and Y. So the net electric field pattern is this one here. That is the net electric field pattern. That is the net electric field pattern. So we continue. We continue. Right, we continue to solve here. We continue to solve. The next question is as follows. This discussion is being recorded, so, but yeah, we're not going to be very long because we're going to be doing a part discussion. So we have a discussion now. We're gonna have another discussion again as well today afternoon. Okay, let's look at the next question, 7.3, but we're gonna do the full question 7. Calculate. Right, calculate the magnitude. The magnitude of the electrostatic. Of the electrostatic force Y. Okay, of the electrostatic force that that Y exerts on X. So let's calculate the magnitude of the electrostatic force that Y exerts on X, and also that X exerts on Y, because it is nothing other than an interaction of these two objects that are in space. And we want to find the magnitude of the electrostatic force between the two objects, the 2-point charges. And this is what we do. So this is KQ1, Q2 over R squared. And this is the formula. So if this is the formula, we substitute. So if you want, you can say Q1, Q2, but in the place of the 1 and 2, we can put X and Y like this. So the charge on X, the charge on Y, divide by the square of the distance between them by the constant of proportionality K. We multiply. Okay, so K is therefore a constant called the proportionality constant, which is 9 by 10 to the 9. Right, so we have the following. So we have, because we need the magnitude, do not put the sign. This is negative, but just put positive because we're interested in the magnitude. 7.2 times 10 to the minus 9. 7.2 times 10 to the minus 9. You divide everything by the square of the distance between them, which is 0.03. So which is 5.18. Times 10 to the minus 4 newtons. Right, so this is the magnitude, and therefore we just write this answer. This is the size of the electrostatic force, and we have written it like this, and it is the answer to the question. Because we have to calculate the magnitude of the electrostatic force that Y exerts on X. That Y exerts on X. So to do this, therefore, we proceed as follows. We have F, which is KQX QI over R squared, which is K 9 times 10 to the 9, 7.2 times 10 to the minus 9, 7.2 times 10 to the minus 9. One charge is negative. X is negative, but we put a positives here because we are interested in the magnitude, not the direction of the force. Not the direction of the force. But now, if the question had said the electrostatic force, they didn't say just magnitude, because the magnitude are the sizes, they have no direction on them. But now, if they want to just, if the examiner had said electrostatic force, we're going to put a negative. A negative force means a force of attraction. That becomes direction. Direction is attraction or repulsion. Okay, so now it's either the two attract each other or they repel each other. But obviously, because at this point, one is negative and the other one is positive, negative and positive attract, but two positives repel and two negatives repel. We're going to look at the electric field pattern in a case like that one. Okay, now just comment on the case like that one. Okay. Right, if somebody would look at a negative and a negative, here is the negative, and here is another negative. So here it is repulsion, they push each other. So this becomes sort of the net electric field pattern. Okay, this one is the net electric field pattern. Now you can have positive. So yeah, it's a diagram like so. And then now if you have positive and positive, also positive and positive repel, this becomes the net electric field pattern when these things repel each other, because positive and positive will like push each other away. They push each other away.
Is that 7.4?
No,
Still 7.3.
I'm just mentioning this. It's not numbered. It's just a comment, because we're done with 7.3. This is the magnitude of the electrostatic force. Okay, so we found the answer, but I'm just commenting now on what we call like charges. Like charges, or if you don't want to say they are like charges, which are sort of same charges. Okay, if there's negative and negative. So the negative, therefore, obviously we have said that they go in these arrows. Okay, literally just a comment. If you have negative, because they can put negative and negative in the exam, and that's my point. If they put negative and negative in the exam, this will be the net electric field pattern for the negative and negative. They will like go in, okay, like this, but they push each other away. So if they say draw the net electric field pattern, this becomes the net electric field pattern. But now here, if it's, what about if it's positive, positive? Because we have seen negative and positive. This becomes the electric field pattern. Okay, these ones attract each other, and the direction of movement is actually such that the arrows are from positive to negative, positive to negative, positive to negative. But at the end here, they just sort of appear to like end in space, end mid-air. Okay, this is negative and positive, and this is the net electric field pattern. Right, so this one becomes the net electric field pattern. Net electric field pattern. Right now, also this becomes the net electric field pattern, but in the case of negative and negative, or positive, positive. So with positive, everything goes out. Out, out, out. Out, 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 out. So with positive and positive, the same or like charges, they go out. Okay, so this becomes again the net electric field pattern in both cases. In both cases, call them the net or the total electric field pattern. Total electric field pattern. Okay, now let's look at 7.4. Okay, this was not asked. They did not say consider positive and negative and negative and positive and positive. They didn't say that. But I'm just commenting on this because it is very, very important. Right, 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 right. So now 7.4. Okay, so 7.4 starts with a diagram. A point charge, a third. A third point charge Z of a known positive charge. Positive charge is positioned, right, is positioned 0.01 meters to the left. To the left of point charge X on the line. Joining point charges X and Y as shown in the diagram. In the diagram below. So there's something called a third point charge Z. A third point charge Z of unknown positive charge is positioned 0.01 meters to the left of point charge X on the line joining point charges X and Y as shown in the diagram below. Let's draw the diagram. Right, so in drawing the diagram here, what we have is we have a horizontal sort of line here, like this. We have a point called Z. Another point, X. And another point, Y. So minus 7.2 times 10 to the minus 9 coulombs. Maybe I can put it up here. See what we can do. Let's put it below. Put it up. Let me see what happens. Minus 7.2 times 10 to the minus 9 coulombs. 7.2 times 10 to the minus 9 coulombs. Okay, let's just keep it that way. Like here, we go down. Okay, this one here. Not 0.01 meters. So we have this one. Not 0.03 meters. Okay, now 7.4. You need to draw a labeled vector diagram to show the directions of the electric field pattern of the electric fields at the point X, or at the point where? At the point where X is positioned right, so draw a labeled vector diagram to show the directions of the electric fields at the point where X is positioned. So now let us look at these, but look at these very carefully. What are we supposed to do? The examiner is asking us, and they asked the students in June last year to draw a labeled vector diagram to show the directions of the electric fields at the point where X is positioned. X is here. We need to draw a vector diagram to show the directions of the electric fields at this point. Direction of the electric fields at this point, but you need to draw a vector diagram. 7.4. Let's look at how the vector diagram was supposed to be drawn in June last year. Obviously, because if this is the case, and you want to draw a vector diagram to show directions of the electric fields at the point where X is positioned. Okay, now let's think together. The electric field at Y. First and foremost, what is happening to these two things? But in which direction is the electric field at point X? Right, in which direction is the electric field at point X? Because first and foremost, you need to know that at that point charge Z of unknown positive charge. So Z is what? Is positive. Right, so we note therefore that Z is positive. And then want to know what is happening with the vector diagram of the electric fields at point X. So if Z is positive and X is itself negative, but Y is positive, what happens to electric fields at X. Draw a labeled Venn diagram to show the directions of the electric fields at the point where X is positioned. So we're gonna actually illustrate the electric fields due to Z. Because Z itself is positive. So the positives, they actually move away. The field lines, the electric fields go out, radiate outwards. Right. For Z is going to be in that direction, and it is consistent with these things I was doing here. Okay, if you have the positives, the electric fields radiate outwards, but with the negatives, they radiate inwards. Inwards, they like go in. Right, so just note that. So now here with the Z, because it's an unknown positive, the fact that it's positive, so the electric field lines would have to do like the many things. So you have to go, you can make them a little bit straight because we're just showing only what is happening here with this one. So with the positives, everything goes out and out. Okay. So with the positive, in principle, we just say these, we just draw something like this if it is just by itself. And we then say everything goes out. The electric fields, the field lines go out like this. Okay, so we're good. So now let's look at the other one. Okay, now this one is what we have sort of get here. Okay, now just take a look at that, but yeah, these are just not connected, please. We're just showing the fact that if it's positive, you could have you have that kind of a pattern here. Okay, everything goes sort of out because it's in a non-positive charge, but it's positive. Okay, now so the electric fields go out, but now let's look at the electric fields at Y. The truth is Y is not different at all. So you're gonna have, because it's positive as well, everything goes out. Positive goes out here, goes out there. Now, what is the examiner looking for here in this question? Okay, because X itself is negative. So negative means everything goes in. Everything goes in because it's negative. Okay, so we're just drawing these things there, so everything goes in because this is sort of the electric field pattern for each of these positive point charges. Now, the examiner is saying, draw a labeled Venn diagram to show directions of the electric fields at the point where X is positioned. What is happening in the middle here? Want to know the electric fields in the middle here. What is happening? Or just at that point X, which is not necessarily at the center. But what we can see clearly is that this goes out and this go out. So this is what we get. So Z, if we actually look at the two things here, Z and Y, because they are both positive, but due to X, Z and X are attracted to each other because it's positive and negative. So the electric fields now, because the electric field itself is a vector, right? So it means that there's going to be a force of attraction here, and the electric field pattern is going to be in this direction for Z. So in other words, there's going to be EZ. And there's going to be EY as well. Y itself is also going to be attracted like this to X. So it's going to move closer to X. So they're going to be moving towards each other. These. So in other words, now this is going to be attracted so that the Y, EY is to the left. And this EZ is moving like this, attracted like this. So Z is moving towards Z. Z is moving towards X, or is moving towards the right. So this is the Venn diagram the examiner wanted. This is all. So it's nothing much there. But just watch the directions and make sure you sort of make sense of these, because it's already there in a few months, this one. Just in May, after April. Okay, let's look at the next question. 7.5. Now, in 7.5, the magnitude of the resultant electric field at the point where X is positioned is 4.91 times 10 to the 3 times 10 to the 5th power times 10 to the 5th power newtons per coulomb. Let's proceed to compute, to calculate the magnitude of charge Z. The magnitude of the resultant electric field at the point where X is positioned. What is the magnitude of the net electric field? But we are not interested in the electric field at the point, but the magnitude or the size of the resultant. Resultant is like net, total electric field at the point where X is positioned is this one. Calculate the magnitude of charge Z. Calculate the magnitude of charge Z. So we're saying effectively the magnitude of the electric field, of the resultant electric field at point X is, at the point where X is positioned, is 4.91 times 10 to the 5th power newtons per coulomb. Calculate the magnitude of charge Z. Okay, let's look at these, but look at these very, very carefully. Look at this very, very carefully. 7.5. 7.5. So the couple of things we need to consider. So we need to consider what is happening here. So we're looking at 7.5. 7.5, but we're looking at the solution to this. Okay, now let's think about this first. I want us to recall something here. Here is Z. Here is X. And here is Y. So we're okay, not point not. Okay, let's look at this. 0.01 meters. Okay, let's make this one dashed as well. I want to make this one a broken line. So we have this. Not 0.03 meters. So now we continue to, okay, this is a sort of the setup that we got. But we actually remember some of the things, like the charge here, we already know that minus 7.2 times 10 to minus 9 coulombs. That is the charge there. 7.2 times 10 to the minus 9 coulombs. Okay. Let us find now the magnitude of charge Z. According to this question, so we're saying the magnitude, or actually, yeah, the magnitude of the resultant electric field at the point X, at the point where X is positioned, is 4 points. Okay, let's just write that one down. Here, at this point, the electric field, the net, in other words, F net, is 4.91 times 10 to the 5th power newtons per coulomb. Newtons per coulomb. So now this is the case. So if this is the case, then if the Fe net, right, resultant electric field, so we call it E net, just call it E net because it's a result, according to this, the magnitude of the resultant electric field at the point where X is positioned is this, 4.91 times 10 to the 5th power. So it is E net this. Okay. And so now let's continue. So which means, therefore, we're going to proceed to then say, if we want to calculate the magnitude of charge Z. Okay, what we'll be able to observe here is that the net electric field is the net electric field now at X, where X is positioned, the net electric field there is due to the fact that you have the net electric field due to Z plus the net electric field due to Y. So the net electric field at X is the net electric field due to Z plus the net electric field due to Y. That is going to give us the net electric field there. Okay. So, alternatively, the net electric field, and in the middle, because this Z is positive, is due to the net electric field at Z Y is associated with, in terms of vector directions, you can write in that particular manner there. You can write that particular manner. Why? Because we have said already, this vector diagram here is in that direction and another one is in that direction. So this one here is EY. And then this one here is EZ. We've already discussed the vector diagram here. So because these are in opposite directions, you actually subtract them as such. Subtract them as such. Okay. What then is all this here? Okay, let's continue to solve this problem. 7.5. Which means that E net is is actually KQZ divided by R squared minus KQY divided by R squared. 4.91 times 10 to the 5th power is equal to 9 times 10 to the 9th power QZ minus 9 times 10 to the 9th power QY, right, which is 7.2. The charge on Y is 7.2 times 10 to the minus 9. And then you divide these by, okay, 0.03. Okay, because we have 0.03 and the charge from Z is 0.01. So this is 0.03. Like this. Right, so this is what we get. This is exactly what we get. 0.03. Okay, we continue. So we square this. Right, so we manipulate this and solve for QZ. This one first is 0.01. So you square this. So as a consequence, it is 0.6.25 times 10 to the minus 9 coulombs. So this becomes sort of the way to do this, but obviously you can do it with a plus here as well. That's sort of you're adding the two. But in terms of vectors, then we subtract these. Okay, we subtract these because each of these is a vector. So if we subtract these, therefore, we're getting the charge on Z, which is exactly what we just got right now. And therefore, this becomes the answer to the question. So this becomes the answer to the question. And so we have answered question 5. Spend some time to think of this, because in 7.5, we're given the magnitude. We're told that the magnitude of the resultant electric field at the point where X is positioned is this one. We're given the net or the resultant electric field as this at X, and then where X is positioned, we're to calculate the magnitude of the charge Z. So the magnitude of the charge Z became exactly this here. Okay, so yeah, we must thank you for joining us. All right, our plan is to meet again in the afternoon, 4 p.m. Right, is to meet again at 4 p.m. So yeah, I hope that there's no load shedding at that time, so we can make the most of our discussion then, looking at more things.